Hi, I want to go over some things that are going to be on the final. First of all, you do need to study the team proof project, parts 1 through 4. So yes, there will be some finite geometry things on the final exam. Which ones? Well, check your first couple team proof projects and you'll see some good things that you need to look at. So I want to encourage you, if you haven't done so, to actually take a real long look at section 2.3. Why? Well, because it sets up, there was this search to determine whether or not to solve the puzzle of Euclid's parallel postulate. For over 2,000 years, they were not sure whether it was a postulate or a theorem. And so it turns out that when you don't have a parallel postulate, that neutral geometry allows both hyperbolic geometry that looks like this over here. Sorry, I'm not getting it to work with me. So hyperbolic geometry looks like that. And Euclidean geometry, of course, has the straighter lines that we're used to. So definitely take a look at the at section 2.3 and read about this story. It's truly important. Okay, and this is one of the key things that rectangles do not even exist in hyperbolic geometry. This idea that you can have a parallelogram with 4 right angles doesn't exist. We have to have a Euclidean geometry for it to be true. Same thing with the Pythagorean theorem. There is no such thing as a squared plus b squared equals c squared until we have a Euclidean geometry. And to have that, we need that Euclidean parallel postulate. Okay, so this quest, it became clear to mathematicians that there was a problem with rectangles if they didn't use a Euclidean parallel postulate. Okay, so you've got Giovanni Saccheri and Johann Lambert. Okay, so Lambert Quadrilateral, you see this quadrilateral with 3 right angles. So they're doing everything they can to make a rectangle. Same thing, Saccheri also tried to make a rectangle. These 2 legs, they're called, on the sides, the left and right sides, are congruent, and both are perpendicular to the base. So it turns out they're parallel to each other, because perpendicularity does work. And so 2 lines perpendicular to the same line are parallel. Okay? But even these 2 rectangles, the Saccheri quadrilateral and the Lambert quadrilateral, even these were not enough by themselves, right? There's Lambert and then Saccheri. Sorry, having trouble scrolling. Okay, and then we have Saccheri. Right, so these quadrilaterals, the guys were doing everything they could to create a rectangle. But rectangles simply do not exist until we have a Euclidean geometry. So therefore, we need Euclid's 5th postulate. Okay, so there's lots of interesting things here, and I just want to say the theorems that were on the problem, on the team proof project, right? 1 and 2 here, and this one, we did number 4. So these 3 theorems, those are good theorems to take a look at prior to the midterm. Okay, definitely take a look at those. And again, read the section because it's really important. So then let's take a look here at section 3.1. Okay, and this picks up the story. Now, we do have more of the story here in Euclidean geometry, and we talk about Bolyai, and there's a nice little chart here about the things that are true in a neutral geometry versus things that are true in Euclidean geometry. So as soon as we get the Euclidean parallel postulate, we get these things here on the right. But these things on the left are things that feel like they'd be true, but are not. Okay, so going into Kea and the results of the parallel postulate. So this is a good, these two sections, 3.0 and 3.1, are definitely good sections to read. Let me point out some theorems that are important. You definitely want to take a look at Theorem 2. But it's a pretty hard. Number 1 and number 2 are not the easiest ones to prove. Nor is the number 3, the Euclidean exterior angle theorem. Okay, so what are we looking at? Definitely take a look at the parallelogram decomposition theorem. Okay, and I also want to point these guys out. They're important. So all of the quadrilaterals, rectangles, rhombi, parallelograms, kites, they all can be defined in terms of their diagonals. Okay? So the diagonals of a quadrilateral bisect each other if and only if the quadrilateral is a parallelogram. And sorry, there should be an if here. I apologize. If and only if. Okay? And exactly one diagonal of a quadrilateral is the perpendicular bisector of the other if and only if the quadrilateral is a kite. So each of these guys, rhombus, parallelogram, square, rectangle, they all have definitions in terms of their diagonals. Okay, in terms of their diagonals. So definitely you want to look at these. Now we proved one of them, although it didn't get proven correctly. And let me show you what I want to talk about here. If and only if theorems. Okay, because this has happened a couple of times this semester, and there's not a good example of it to study for you guys. So I'm going to have to tell you, you need to look at how to prove an if and only if theorem. There will be one on the midterm. Okay, so let's look at number 5 here. The diagonals of a quadrilateral bisect each other if and only if the quadrilateral is a parallelogram. Okay, so you'll see this symbol, the double arrow symbol, to also mean if and only if, and then we prove it in one direction or the other. So this actually, to prove an if and only if theorem, we actually require 2 full proofs. Okay, so what are we going to start with? All right, we are going to start with, suppose it's a parallelogram. Prove that for, and so we need to prove this for all parallelograms. So what are we going to do? We're going to assume, right, that there's some random parallelogram, right? Let it be chosen and be arbitrary. Okay, so give me an arbitrary parallelogram, and then what am I going to do? I'm going to prove that its diagonals bisect each other. Okay, so that's proving it in one direction. And then I'm going to prove it in the other direction. So I'm going to do that complete proof, and then I'm going to start on the other proof where I assume that it's a quadrilateral whose diagonals bisect each other. And from there, using only those assumptions, I'm going to prove that that indeed forces it to be a parallelogram. So think about that. If I'm doing an if and only if proof, there are 2 full proofs to do. If I'm doing an if and only if proof, there are 2 full proofs to do, and you need to show some knowledge of that when on the midterm. There will be an if and only if construction on the midterm. Okay, and then the final thing I want to talk about is section 3.2. This is the parallel lines section, and this has a couple great theorems. This median concurrence theorem is an important one. That if I join the medians of a triangle, they do meet in a single point. It's not the easiest thing to prove, but it can be proven. And that's how we find the median. And we also have a couple of other triangle center, the ortho center. We've got the median concurrence. So why am I mentioning this? Well, I was going to go down here. Oh, and this transversal congruence lemma. So just take a look at this. Suppose I have 3 parallel lines, and this line T is a transversal, and as it goes across these three parallel lines, it turns out that B is the midpoint of AC. So the line segment AB and the line segment BC are congruent. If that's true, then it will be true for any other transversal that cuts these three parallel lines. It will divide into two congruent line segments, just like you see here with transversal M. Okay? Or am I going to ask you to prove that? No, I mean, it's not terribly hard. You kind of see the proof here. You create a perpendicular. Why do you need a perpendicular? Well, you want a perpendicular so that you can use your, you can get these angles congruent. That's one way to go about it. But you basically need to prove something about these triangles. And we're using that, we're using the theorem that parallel lines are everywhere perpendicular. But anyway, so it's not the world's hardest thing to prove, but there's not going to be one like this on the exam, on the midterm. Okay, now the transversal congruence theorem. So now this says, well, if I have 18 lines that break down in such a way that all the line segments created are congruent, then that will be true for any transversal that cuts them. So no, you're not going to have to prove the median concurrence theorem or the transversal congruence theorem. Okay, what will you need to prove? This is a good one. Two lines parallel to another line are parallel to each other. If a line intersects one of two parallel lines, then it intersects the other. And I am not going to ask you to prove this one. This one's a little wonky, so I won't require you to prove that. So there, I've gone over 3 sections and kind of highlighted the types of theorems that that might be on the midterm, so you want to take a look at those. Remember to look back through your team proof projects, because those proofs are possible questions that will be on the midterm. And also remember that we haven't really seen a good example of an if and only if proof. And there is going to be one on the midterm. So I want you to think about how to prove that and recall the fact that it requires 2 complete proofs. Okay, I'll be back tomorrow with more hints about how to study for the midterm.